Hello, we are continuing Chapter 17, Thermochemistry, and we are looking at calculating heat in different situations. And so today we're going to talk about phase changes. So we have solids, liquids, and gases. And we know that solids are the lowest in potential energy. Close to them are the liquids, just a little bit higher in potential energy. And then gases have very, very high potential energy relatively. So let's review the different phase changes. So going from a solid to a liquid, that is melting. Other way around would be freezing. Going from liquid to gas would be vaporization. Going the other way around would be condensation. And then remember, going from solid straight to gas, that is sublimation. And then the opposite direction, that is deposition. So anytime you have a phase change where you are going down in potential energy, so going from a gas to a liquid, or a gas to a solid, or a solid to a liquid, you're going from a high potential energy to a lower potential energy, your substance has to release that extra energy, and so that would be an exothermic process. So condensation, freezing, and deposition are all exothermic. Whereas if you are going the other way, so you're going up in energy, so from solid to liquid, melting, or from liquid to gas, vaporization, or from solid to gas, you're going from a low potential energy to a higher potential energy, so your substance has to absorb that difference in energy, and so those would be endothermic. So sublimation, evaporation, and melting would be endothermic, whereas freezing, condensation, and deposition would be exothermic. So let's review our heating and cooling curves that we've studied before. And so this is the heating curve. So if you have a solid at below its freezing point and you start heating it, first its temperature would rise up, so you have an increase in kinetic energy. Then it's going to start melting, so you have an increase in potential energy. And then you're going to see that the temperature will start rising again, and that would be an increase in kinetic energy. Then it's going to start vaporizing, turning into a gas, which is a change in potential energy, the position of the particles. And then you're going to see that gas heat up to a higher temperature, so another kinetic energy change. Cooling would be the exact same thing, but opposite. So this would be gas above its boiling point. This is a gas at its boiling point, liquid at its boiling point, liquid at its freezing point, solid at its freezing point, and solid below its freezing point or melting point. So let's say I take some ice and I want to melt it. So I'm right here. And I try to calculate the change in energy. So I have some ice. I give it some energy, so that ice is absorbing energy. I want to calculate how much energy is absorbing in order to get it to melt. So we've learned that to calculate the amount of heat that is transferred, you do Q equals mc delta T. Well, in this case, right along here, Q equals mc delta T is not going to work. Why not? Because delta T here is 0. So when you plug it in, anything times 0 is going to be 0. You're going to calculate that the change in heat is equal to 0, which we know is not true, right? If I'm melting ice, it's absorbing heat. So I want to calculate how much that is. And so where you have a temperature change, you can use Q equals mc delta T. But if you have a phase change, you can't do that. So what did they do? Well, they got a certain amount of ice, and let's say a mole of ice, and they gave it little bits of energy at a time, measuring how much energy they keep adding until it just melted. And they call that the molar heat of fusion. So it is the heat that's absorbed by 1 mole of your substance as it melts from solid to liquid at constant temperature. And they were able to figure out what that amount of heat is because they kept adding until it just melted. They call that the molar heat of fusion. It is the heat that is needed for 1 mole of your substance to melt. Fusion means melting. Well, similarly, there's molar heat of solidification. That is the heat that is transferred when 1 mole of your substance solidifies. That means freeze. So turn from liquid to solid. Those two numbers should be exactly the same, except one is endothermic and one is exothermic. Melting is endo, freezing is exo. For water to go from solid to liquid to melt 1 mole, it takes 6.01 kilojoules of energy. It has to absorb that much energy in order to melt. To take liquid water and freeze it, the liquid water will release 6.01 kilojoules per mole. So those numbers are the same, except one is endothermic, one is exothermic. These numbers, the 6.01 kilojoules per mole and negative 6.01 kilojoules per mole, those are going to be provided to you on the test to be able to use. Similarly, we have molar heat of vaporization. So that would be the amount of heat, the amount of joules or kilojoules that is needed for 1 mole of your substance to vaporize, turn from liquid to gas. And we have molar heat of condensation, the amount of heat that's transferred when 1 mole of your substance condenses, goes from gas to liquid. Those two numbers should be the same, except one is positive, endothermic, and one is negative, that's exothermic. So for water, the amount of heat that the liquid has to absorb in order to become gas is 40.7 kilojoules for every mole. And the amount of heat that's released when the gas condenses to liquid water is 40.7 kilojoules for every mole. In this case, we're releasing it. In this case, we are absorbing it. Notice that, again, those numbers will be given to you on the test. Notice that the heat of vaporization or condensation is much larger than the heat of melting or fusion. Why is that? Well, that's because this is potential energy that's different, right? Along those lines here, you're not changing the temperature, you're changing the potential energy, the position of the particles. In a solid, you have this tight crystal. In a liquid, you're breaking that crystal, moving the particles around. In a gas, you're separating the particles. So the position of the particles is changing along phase changes. The position of the particles in a solid and in a liquid is very, very similar. So it doesn't take very much energy to change from one to the other. Versus the position of the gas and the liquid phases is very differently, drastically different, so it takes a lot of energy to change it. So notice that vaporization and condensation takes a lot more energy than freezing or melting. So how do we use these? So going back to our cooling and heating curves here. So here we're going to use molar heat of fusion, and same thing here, molar heat of fusion. Remember, fusion or solidification, I guess. Same thing here, you're going to use molar heat of vaporization, molar heat of vaporization or condensation, right? And so along these lines, you're going to use these molar heats of fusion or condensation or vaporization or solidification. But along the lines where you have a change in kinetic energy, so all these, you're going to use Q equals MC delta T. So when you're given a problem where you're, let's say, heating water or cooling water, you need to figure out where are you on this heating curve or cooling curve. And if you're somewhere where the kinetic energy is changing, and you know that because the temperature is changing, but you have the same phase, then use Q equals MC delta T. But if you have a state change, a phase change, but no temperature change, then you use these molar heats of fusion or condensation or whatever. Some problems are going to be given to you where you're only at one of these steps, so you're going to do one calculation, or you could be given 2 steps, or 3, or 4, or all 5. So I could tell you, hey, I have ice at -20 Celsius, and I'm going to heat it up until I get to liquid at 20 Celsius. Well, that's 3 steps, right? You got to do a Q equals MC delta T here, then a heat of fusion here, and then an MC delta T here, and then you add them all up. So let's look at some examples and try to solve them. So let's start with this one here. It says we want to calculate the energy required to raise the temperature of 75 grams of water vapor from 125 Celsius to 139 Celsius. So 125 Celsius, it's in the gas form. 139 Celsius, it's also in the gas form. So here we are just increasing the temperature without increasing the phase. So looking back at our heating curve here, we are right there. This is where we're starting, and this is where we're ending. So it's just one step. And in that step, we're going to use Q equals MC delta T. So let's do that. So we're going to say Q is equal to MC delta T because this is a temperature change, not a phase change. So Q is equal to 75 grams. C, watch out because this is water vapor, not liquid water. And so we need to look up the value for the C for water vapor. And if you look at your table of the specific heat capacities, you'll see that ice is 2.093, steam is 2.009 joules per gram Celsius. Is different from water, so you have to be careful with that. And then delta T is final minus initial, so 139 Celsius minus 125 Celsius, and we're gonna calculate that. So I got Q to be, we need 266, so 2100 joules. My grams cancel, my Celsius cancels, and I end up with joules. So that is my answer. So we've done this before, MC delta T. The only trick here is to be careful that this is for water vapor. Okay, let's look at the second example. Second example says, how much heat is absorbed when 24.8 grams of liquid water at 100 Celsius is converted to steam at 100 Celsius? So we'll see that our temperature is not changing, but we have a phase change in this case. So we're going to use molar heat of something. In this case, we are going from liquid to gas, so that would be molar heat of vaporization. And we know that the molar heat of vaporization is 40.7 kilojoules per mole for water. So let's look back at our heating and cooling curve here. We are vaporizing, so we are starting here and we're ending right there. So that is a one-step problem. So again, we're going to use molar heat of vaporization. So how would we do that? Well, we're given 24.8 grams. And we know that we want to find heat, so we want to find joules or kilojoules, right? And we know that it's 40.7 kilojoules for every 1 mole. So I would want to change my grams to moles. So we'll put grams of water here, moles of water here. To go from grams to moles, use the molar mass. That gets you to moles of water. And then you put moles here so they cancel. Kilojoules here, and we know that it takes 40.7 kilojoules for every 1 mole of water. And that's going to give you how much heat is absorbed in order to vaporize that much water. You get 56.1 kilojoules. Okay, let's try the third problem. It says calculate the energy required to melt 10 grams of ice at negative 10 Celsius. I believe that's what that says there. Oops. And take it to 150 Celsius. So we are actually doing multiple things. Our temperature is changing, right? We're going from -10 to 150, but also we are going through some phase changes. We have ice, and we're going to go all the way to 150 Celsius, which means we're going to have gaseous water, right? So let's look back at our heating curve here. We have ice at -10, so we're somewhere here. We need to go to 150, so all the way up here. How many steps is that? That's 1, 2, 3, 4, 5 steps. So when you're doing a problem where you have multiple steps, 2 or 3 or 4 or 5, you really want to write down your steps first. So I'm going to plot my, this is 100 Celsius, or sorry, 0 Celsius. This right here is 100 Celsius. This is just my heating curve. So I'm going from -10 Celsius all the way to 150 Celsius. Okay, so let's write our steps first. So our first step, we're going from solid at -10 Celsius. We're going to take it to solid at 0 Celsius first. So that's this step right here, right? That is until we get there. Our next step is to go from solid at 0, right here, that would be melting, until we get to liquid at 0. So from solid at 0 to get to liquid at 0. So right now we're here. Next, our water is going to heat up, and its temperature is going to change until we get to liquid at 100. So we're going to go from liquid at 0 to liquid at 100 Celsius. So right there. And then next, we're going to go from liquid at 100 to gas at 100. So this is vaporization right here. Liquid at 100 Celsius to gas at 100 Celsius. And then finally, we're going to go from gas at 100 and change its temperature until we get to gas at 150. So the first step is write down your steps. Okay. Then we're going to calculate the heat for each of these 5 steps, and then we're going to add them all up together. So let's start with this first step, which is a change in temperature. So we're going to do Q equals MC delta T. So our mass is 10.0 grams. Our C for ice is, let's look that up, 2.093 grams, or sorry, joules per gram Celsius, times delta T. When you do delta T, you only do it for the one step that you're doing. So my final is 0, my initial is -10, so 0 minus -10 would be +10 Celsius. Then we add our next step, which is this right here, is melting. So we're going to use delta H of fusion in this case. We're given 10 grams. We're going to convert that to moles. 1 mole is 18.0 grams. And then we're going to say it is 6.01 kilojoules for every 1 mole. Now, the only problem right here is that this answer is going to be in joules, right? My grams and grams cancel, my Celsius and Celsius cancel, so I end up with joules. But this right here will give me kilojoules. So I need to convert one or the other. I can't add up joules with kilojoules together. So I need to change all of them to joules or all of them to kilojoules. I'm going to go ahead and change all of them to joules. So I'm going to add a step here. I'm going to say 1 kilojoule is 1,000 joules. Okay, my next step. Liquid at 0 to liquid at 100. This is a Q equals MC delta T because I'm changing in my temperature. So temperature change or phase change is what you want to ask yourself. So temperature change, so Q equals MC delta T. So 10.0 grams. C for liquid water is 4.186 joules per gram Celsius. Delta T would be 100 minus 0, which would be 100 Celsius. Plus, next step is this right here, which is vaporization. So we're going to use heat of vaporization. So 10.0 grams, change that to moles. Then we're going to say it's 40.7 kilojoules for every mole, but then go from kilojoules to joules. And then finally, the last step, which is this step right here, going from gas at 100 to gas at 150, that's a temperature change. So we're going to use MC delta T, so 10.0 grams. C for water vapor is 2.009 joules per gram Celsius. Delta Z would be 150 minus 100, which is 50 Celsius. You add all these up together, and that will give you the answer. If you are doing this correctly, all of your steps should either all be positive or all be negative. You can't have one step that's negative and one step that's positive, because either you're heating it, which means it's absorbing energy, so it's going to be positive, or you're cooling it, so you're releasing energy, so it's going to be negative. So I'm going to pause for a second to calculate it. So I ended up with 31,300 joules. Now, sig figs can be tricky with this because you have to figure out the sig figs in each of them. These are all multiplication and division, so you go by number of sig figs, so they should all have 3 sig figs in their answers. But then when you add them together, you got to go by decimal places. And so this is to the ones, this is to the tens, this is to the tens, this is to the hundreds, this is to the hundreds, and so your answer should be to the hundreds as well. And so that would be the correct sig figs. It's a little bit tricky with the sig figs here, so with these ones where there's a lot of different steps, I will be a little bit more flexible with sig figs.